Okay, we're gonna combine 13.1 and 13.2 together. Curves in space, tangents, derivatives, and integrations. So, a particle in a plane can be described by a vector. And this is normally parametric equation, if you recall. This is from trig. So if you're given y equal f of x, you can describe this by one of two things. Either a parametric equation, let x equal t and y would be f of t, or by a vector, ti f of tj. Example, and we're going to do a lot more examples later on, I just want to get this out of the way. Example, y equal x squared. If you glance at this, well, we know what that graph looks like. That graph looks like, so in rectangular coordinates, that's nothing more than our famous parabola. There it is. Now, I could describe that two more different ways, and we should be able to really do all three. Parametric equations would be something that you did back in the days. The new would be a vector equation, which is really a parametric equation, because when we go to 3D, things are going to differ a bit more. So I could say, you know what? We could let x equal t, and y would be t squared. That will work. In this case, the difference... Oh, it's off. I didn't see that. Okay, so if I let t equal 0, well, t equals 0 will be x is 0, y is 0. I'm right here right now. 1 minute from now, I'm gonna be right there, which indicates, and a minute ago, I was right here, which means the direction. So anytime you're using parametric equations, you must have direction. And if I describe this using a vector, each has its own application. If I say, well, look, r of t is actually tt squared, which is identical to the parametric. That's why when we went over how to find an equation, I really emphasized a lot on vector equation because they go hand in hand. The difference, however, is that at t equals 0, I have r of 0 being 0, 0. Well, you're right there. T equal 2. R of 2 is going to be 2, 4. 2, 4. So this is going to be described now by a bunch of vectors. And you would say that's r of 2. R of t equal negative 1. R of negative 1 is negative 1, 1. So again, each has its own application, and that is r of negative 1. And you need to know all three. Now, in 3D, in space, things are slightly different. R is given as f of t, g of t, and h of t. It might not be as easy as you think to come up with such relation. But in 2D, you can. If you want to take the limit as t approaches b of this vector, well, that's simple. Take the limit of the components, provided the limit exists. If those components f, g, and h are differentiable, then taking a derivative of r is simply taking the derivative of the components, and if f, g, and h are continuous on interval from a to b, then when you integrate this vector, you simply integrate each of those components. And that's pretty much it. So let's talk about a few examples. First, let's talk about domain of a vector function. Something new, but the term isn't new. The domain, you already know how it works. The domain for this vector R must be satisfying the I, the j, and the h component. I'm so tempted to say k. I'm so stuck in k. So, t cubed has no restriction. The radical. This indicates that t must be bigger than or equal to 0. So far, I have that restriction. The fractional part, 3t divided by t minus 5. Well, I know that t cannot equal 5. So my domain, anytime I have multiple restrictions, I put that on a number line. That's the number line t. The first one says t must be bigger than or equal to 0. And this says take 5 out. So domain would be what? 0 to 5 union with 5 to infinity. That would be the domain for this vector function. Find the limit. That would be the limit as t approaches 0 of t squared over sine of t, the limit as t approaches 0 of the tan of t, and the limit as t approaches 0 of e to the t minus 1 over t. Here I'm getting 0 over 0, so by L'Hopital, this will be the limit as t approaches 0 of 2t over cosine of t. Here, I'll simply get 0, that's done. And here, if I throw 0 in, 1 minus 1, 0 over 0 by L'Hopital. Every time you use L'Hopital, you have to use that h, indicating what you're doing. And now, if I throw 0 in, I'll get 0 over 1, which is 0, 0. And if I throw 0 in, I'll get 1 over 1, which is 1, and that would be my answer. Same deal with this problem. I'll take the limit as t approaches infinity of the square root of t minus 1 over t squared, the limit as t approaches infinity of t over e to the t, and the limit as t approaches infinity of t squared over 3t squared plus 1. Here, since I'm going to get infinity over infinity, I'm going to get infinity over infinity for all of those, I could say L'Hopital applies to all of them. That's going to be the limit as t approaches infinity of 1 over twice the square root of t minus 1 over 2t, limit as t approaches infinity of 1 over e to the t, limit as t approaches infinity of 2t over 6t. This is 1/3, that's easy. E approaches infinity, that approaches 0, that's simple. This piece, that's really the limit as t approaches infinity of 1 over 4t, the square root of t minus 1. As t approaches infinity, that approaches a 0. And there it is. Now, describe the curve geometrically. If I want to describe this geometrically, indicate the direction. This is a vector equation? Well, if I want to describe it geometrically, I'm really trying to figure out x equal t and y equal the square root of t minus 3, which indicates if I put an x in there, this is really saying, out of both of those, this is saying y equal the square root of x minus 3. I know what this is the graph of. This is the graph of 1, 2, 3, a radical raised. Oh, let me fix that. That's what I meant. I'm sorry. So, a radical shifted 3 units to the left, right? Now, at t equals 0, again, couple of points to figure out direction. At t equals 0, I notice I am at the point 0, 2. I'm right here, right now. At t equal -3. 3 minutes ago, I was at -3, 0. -3, 0 is right there. So the direction runs always in the increasing value of t. I'm going to move this graph and put it right there. With this problem, well, I know that x equal 4 the cosine of t, which means x over 4 equal cosine of t, square both sides. I know that from calculus or trigonometry. And z equal the sine of t, which means z squared equals sine squared of t. So this is saying x squared over 16 plus z squared equals a 1. And y is always 3. In 3D, what this indicates, y is fixed at 3, 1, 2, 3. Here I am. And from that, I'm going to move 4 in the x and 1 in the z. And I have this ellipse. Now, at t equals 0, where am I? I am at 4, 3, 0. 4, 3, 0. I'm right here. How about at t equal 1.57 seconds? I am at 0, 3, 1. 0, 3, 1. I'm right here. So I get the direction. This runs in this direction. And if I look at the third example, well, that's the same as part B. But what I notice is that in this case, y is not fixed. So that's still going to say x squared over 16 equal the cosine squared of t. Z squared is going to equal sine squared of t. This is still saying x squared over 16 plus z squared equal a 1, but y equals a t. Since y is not fixed here and it could be anywhere, what that's going to do, at 0, if you look at 0, so I'm going to have 1, 2, 3, 4, 1, 2, 3, 4, 1, and 1. at t equal 3, at t equal negative. So that's going to create a cylinder. But the path is along the cylinder. You're not getting the whole surface of that. Right? But at any given point, I know that this is 4 units. And that is 1 unit up, 1 unit down. At t equals 0, for example, I am at 400. 400. Here I am right now. At pi in 1.57 seconds, I'm going to be at 0, 1.571. 0, 1.571. I'm right here. In 3.14 seconds, I'm going to be at negative 4, 3.140. Negative 4, there's negative 4. So the path is really going to be on this, and obviously it's going to come from backwards. So it's like a spring. Alright? And that's how it works. And you can get direction as well. A bit tougher to do in 3D, but that's how we'll do those. At what point does this particle intersect this? Well, let's see how that works. This is the same graph as I did, except I manipulated that a bit. This is now x squared over 16 equal cosine squared of t, and y squared over 16 equal sine squared of t, which means x squared over 16 plus y squared over 16 equals a 1. Right? And t, z is varying. What that does, that really creates a cylinder. The path of this particle is a cylinder, but it's running in the so the particle is running along this path. And the sphere with 5, the sphere, so you notice on the inside it's not going to touch. As this path is running up, as this is running up, at t equals 0, for example, you are at 400. You're right here. You are along that, right? And at t equal pi over 2, you are at 0, 4 pi over 2. 0, 4 pi over 2. You're right here. So this is running. Do you see what's going to happen? And this is going to come from the bottom, obviously. So the path runs this way. To figure out where they intersect, what you do, you substitute. You take, okay, we do this algebraically. We say, look, throw this in for x, this in for y. Isn't that how we find the intersections? So that is 16 the cosine squared of t, plus 16 the sine squared of t, plus t squared equals 25. This is 16 into cosine squared of t plus sine squared of t. This is a 1. 16 plus t squared equals 25. t squared equals a 9, t equals plus or minus 3. So I could figure out exactly when that happens. R of 3, that would be for the cosine of 3, for the sine of 3 and 3, and R of negative 3, that is for the cosine of 3. Cosine is an even function, it absorbs the negative. Negative for the sine of 3 and negative 3. And that gives you the exact, if you throw this in a calculator, that tells you exactly where that is gonna happen. So a spring is running into a soccer ball. Well, it's gonna enter at one point, but then as you rotate, it's only one entry. That's t equal negative 3. And as it rotates through the soccer ball, as you're rotating that, it's gonna exit out of one point. I'm not sure where that is. That would be wherever this point is. If I plug this in my calculator, that will give me a point on this vector, and it's gonna be matching with this sphere. Now comes the fun part. Given a vector, to find the velocity of the vector, you take a derivative. What's associated with velocity is direction. That's a big deal. If I figure out the tangent, the direction of the tangent tells me the path of the actual particle. So, acceleration is of course the second derivative, and speed is the magnitude of v of t, which is r prime. And we already talked about how to take a derivative, right? How do you take a derivative? You just take a derivative of the components. So, here, sketch the curve, okay? Find the velocity and acceleration and speed. Sketch all of those on the curve. Well, okay, let's see how that works. Here, part I want to sketch the curve. It says x equal t cubed, y equal t squared, which indicates that t equal the cube root of x. So here, y equal the cube root of x squared. By the way, in case you're not familiar with that, so cube root, y equal cube root of x is a graph that looks like a radical and minus that. 0, 0, 1, 1. And the square, it'll take that negative and reflect it. That's what the graph looks like. Now, notice I'm not really putting in the direction yet. And I'm going to show you why. This is I. Now, when I go for the second part, I would say, all right, well, velocity that's the derivative of this. What's the derivative? Derivative is 3t squared and 2t. Acceleration, that is 6t2. And speed general is the square root of 3t squared plus 2t squared. You could do it that way. Now, evaluate it at t equal 1. At t equal 1, I'm really looking at 3, 2. I'm really looking at 6, 2. And I'm really looking at the square root of 3 squared, 9 plus 2 squared, which is 4, square root of 13. Got everything. Now put them on the graph. Here's the deal. Even though it doesn't say, I need r of 1 to get on the curve. I need r of 1. That's 1, 1. So this is really how it looks. R of 1 puts you on it. Now, V of 1 is 3, 2. From where? From this point, I'm going to move 1, 2, 3, 1, 2. From this point, you must be on the curve, not from the origin. Do you see which direction is the velocity? That tells me the direction of the curve. I could pick different values of t, but that's one way of figuring that out. And if I want to figure out the acceleration, that was 6, 2. From this point, 6, there's the acceleration. That's velocity. And there it is.